In this chapter, we will be reviewing and introducing some ideas in statistics. In this lesson, we'll be introducing you to the normal distribution and to z-scores.
Okay, hi everybody. So in this lesson, we're going to talk about the normal distribution and z-scores. So actually, we're going to move you a kind of a big jump ahead here. We're going to start talking about some predictive tools that you can use with statistics and some things that statisticians actually refer back to. Okay, and you should recognize some of this, even if you haven't specifically looked at it before. You hear about this sort of a thing a lot. You just can't help it. It's kind of out there. It's the background noise all around you here. So, for example, if you've got a characteristic, some sort of physical characteristic or whatever that you're measuring, it doesn't really have to be physical characteristics, I suspect, but that's an easy one, like the heights of students, okay, or let's say it's the time taken to complete an assignment. If you've got enough people that you're in your population that you're studying, there's going to be a few, for example, that are in terms of heights, there's going to be a few that are quite short, there's going to be a few that are quite tall, but most people are going to be grouped around the average height. Most people, when they're doing their assignments, some are going to be really, really quick, some are going to take a really long time, but most people are going to be gathered around the average, okay? And so that's what this is what the graphs tend to look like. And what we can do here is we can draw a bit of a curve through these rectangles that we create. Now, the more rectangles you put in here, like if I was to throw in some more here, what you would find is that this particular curve, okay, becomes more and more obvious. Okay, up here, maybe you're not seeing like a really nice curve. Like this looks a little bit more like a straight line and a straight line, and this sort of is too here. But if you've got, if you take the width of the rectangles and make them smaller, because now remember what this is doing, okay, over here. What this is doing here is, this bar graph here is saying that for students that take 10 minutes here, there's like a little over 5 students doing that, right? This is the frequency, okay, the number of students that have this particular statistic here that are doing their assignment in this particular time here. Well, if you make that time frame a little bit smaller, okay, make these rectangles a little bit smaller, you get a lot more of them, and when you connect them, you get this curve a lot more clearly. Now, this is where you've probably heard this before. Okay, this is referred to as the normal distribution curve. Maybe you haven't heard that one, but you've probably heard of the bell curve. Okay, that just gets thrown around a lot. Okay, and it's often used, like it says here, for statisticians to make predictions. Okay, it's got this beautifully predictable curve, and in fact, what's really amazing about it is it almost doesn't really matter what sort of statistic you're taking. If you've got a large enough number of individuals in the population, it tends to follow this kind of a curve. Like in a lot of cases, that's what it does, which is why we tend to call it the normal distribution, or these things tend to be normally distributed. People, statistics that you take about people tend to be normally distributed. Now let's talk about some of the properties of that particular curve that we can use to make predictions, okay? The data centers around the mean, okay? So right here in the center here, right there, this would be the mean of the population. The vertical axis is always the frequency, and the horizontal axis is always the type of data. It's always with reference to the statistic that you're taking here, okay? Or I shouldn't say the statistic, the property of the population that you're studying here. It's evenly distributed on both sides, okay? So basically, 50% of the graph is below the mean, 50% is above the mean, but 100% of the graph, okay, is going to be covered by this curve. And something that it doesn't say right here, but we're going to get into later on here, the area below the curve is equal to probability. Oops, probability. Wanted to put another P in there. Probability, okay? Area below the curve is equivalent to probability. And I'll make a little bit more of an issue about that in just a little bit here. Now, another thing that we do with this normal distribution, this nice little curve here, okay, is we chop it up into some regular bits here, and this is how we do it, okay? we use the standard deviation as our cutting tool in a sense here. So we know that the data is distributed about the mean. And then what we do is we chop it up into little bits here. Now I had explained to you guys before that standard deviation is roughly the distance from the middle out to the point where the curve tends to change directions, where it's a downward curve to an upward curve. So right around there. So that's the width, that's the size of the standard deviation. But what we do is we tend to use it a few more times here, and we break this thing up a little bit more. So this line right here is going to be the mean, starting here, plus the standard deviation. So from here to here is a standard deviation. And then we do it again. Okay, another standard deviation over, and then another standard deviation over. And we just keep adding standard deviations to the mean. Or we go this way and we subtract standard deviations every time here. It's a convenient thing to do. It's a convenient tool to use here. And we have found that when you do that, it breaks up the curve into some very predictable percentages. Okay? And we'll take a look at that in a little bit more detail later on here. But before we get that, we want to kind of work with this idea a little bit more. So we're going to take a look at some examples here. Okay. So this question here, this is like a classic. Almost every time I open up a textbook, you get some variation of this, okay? A nurse records the number of hours an infant sleeps during the day. He then records the data on a normal distribution curve shown below, and then you've got the values here, okay? And the values shown on the horizontal axis differ by 1 standard deviation here. Okay, so here's our graph, here's the data, and we know that each one of these things is jumping up by a standard deviation. So what's the mean of the data? Well, the mean of the data is going to run right down the center here. So the mean of this data would be 13 hours. Okay, so the average infant here is sleeping 13 hours. What's the mode of the data? Now, we didn't really talk about that before, but when you've got a normal distribution, okay, the mean equals the mode equals the median. This is one of those defining characteristics of a normal distribution. So when we say that the mean is 13 hours, we also mean that the mode is 13 hours. Okay? Now bear in mind, that's not true for small populations. You got to have enough. So this would have to have been a study that would have been done with a lot of infants, okay, before you'd start to see this kind of a curve. You can't have like 5 or 6 and start talking about the normal distribution. That's really not enough. Determine the values of A, B, C, and D. Okay. Well, actually, I should do this in order here. A, B, C is up here. What's the median of the data? Well, we just made that comment here. It's got to be 13 hours. Right down the center. We're peaking up there. That's why it's the mode. Okay, and so on. What is the standard deviation? Well, we were told that this was broken up into pieces. It jumps up in terms of standard deviation. So the distance from this point to this one is a standard deviation. So we can tell that that's going to be 2 hours. So then what are the values of A, B, C, and D? Well, I'm just going to add and subtract 2 hours. So to go backwards here, I'm going to subtract 2, and I'm going to subtract 2. And then to go forward here, I'll add 2 and add 2. So B, because that's going to be easier to do, 11 minus 2 is going to be 9. And then to get A is going to be 7. And then starting at 15, this is going to be quite a bit easier. So C is going to be 17 hours, and then D is going to be 19 hours. Okay? Just adding and subtracting the 2 that we were told basically was the standard deviation. Okay, in this question, it says the life expectancy graphs of 3 different brands of light bulbs are shown below, and we're going to assume the same scale is used, so we're not trying to fool anybody here. And we just want to arrange these graphs here, light bulb A, B, and C, in terms of the smallest to largest standard deviation. Okay, now remember that the standard deviation is a measure of the spread of the data, and it's the width from the mean to about the point where the graph starts to change direction here. So here's a standard deviation. I should have started from this one here, but this one was just the easiest one to go to. This is a standard deviation, and right there, that's a standard deviation. Okay? Now, roughly speaking, in terms of the spread of the data, if we assume that the population is fairly constant, think about what you'd have to do. To get a high peak right here, you almost have to squeeze this in, okay, pinch it, to get it to spike. Like if you treat this as if it's a ball of clay, so you can't add more to it, you can't take away from it, sort of thing. Like your population is set. To get it to peak, you have to squeeze it in. If you want a low peak here, you push it down, and then that pushes it out. Okay, so really, it is about the width here, but you can also think about it in terms of the peak here. So which one has the smallest standard deviation? Well, that's got to be B. C, even if you're messing this up here, C is kind of in between both of those two, so C was going to be in the middle regardless. But A here is going to have the largest standard deviation. The width at the center is going to be largest here, which means it has the largest spread. Okay, so if you make predictions here based around the mean, you're going to be fairly accurate. But if you're making predictions here based on the mean, there's a lot more spread to this data, so you're less likely to be accurate with a prediction based on this set of data. Okay, so in this question we read that the marks on a creative writing assignment in English are normally distributed with a mean of 70 and a standard deviation of 6. So we're supposed to complete the diagram below. Okay, now what they mean by that is we're supposed to assume that these vertical lines here are chopping this thing up in terms of the standard deviation. So from here, from the mean, we're going to go up 6. So this would be 76. Add another 6, this would be 82. Add another 6, that would be 88. And I really can't see much beyond that, so it's hard to tell. Going backwards here, if you subtract 6 from 70, you're going to get 64. Subtract 6 again, you're going to get 58. Subtract 6 again, you'll get 52. Okay, so there we are with the marks, okay, in our distribution here. Now let's take a look at the questions we're being asked. What percentage of the class got below 70% on their assignment? Okay, below 70%. I'm asking you, what percentage, what fraction of the population is this piece right here? Well, that's 50%. Okay, half of the population is going to get below the average. Now, just want you to think about it. In your classroom, okay, if you've got like an average sized classroom, it's probably not true that half of the students got below average. It's probably close, but it's likely not exactly true because there's not enough data there. Okay, we talked about this before, where the mean, the average that you'd normally talk about, the mean, is sensitive to outliers. So if you've got one or two students in the class that, for example, got a really low mark on an assignment, that tends to pull the average down to the point where you might not have an even split of the number of people on both sides. But if you've got a large enough group, so like if you're at a university class where there might be hundreds of people in one class, this is more likely to be true. Okay, sorry to kind of go off on a tangent there, but anyway. If there are 30 people in the classroom, how many people got above 70%? Well, again, 30 people is probably not enough for this to be a normal distribution, but assuming that it is, half of the people got above 70, so that's 0.5 of that population. Well, we know that's going to be 15. So 15 students would have gotten above 70%. Now, why is it not possible yet to determine what percentage of people got honors or above 80% in their assignment? Well, 80 is going to be right here. 80 is right here in terms of our marks here. And so what I'm looking for is what percentage of the people got above 80. I want to know what percentage of the people fall into this little category right there, this little tail end. Well, right now I haven't got the tool to tell me what these percentages are. All we know at this point here is that 50% is above the mean, 50% is below the mean. Okay. Now I've suggested a little bit earlier that these standard deviations break this thing up into a nice predictable set of percentages, but I didn't tell you what those were. And even if I did, 80 isn't on one of those lines. It's kind of partway between two cuts here, where I'm using the standard deviation, up one standard deviation. I'm not quite up another standard deviation. Okay, so at this point here, we simply don't have the information. Okay, we don't know the percentage breakdowns here yet. Okay, and in fact, the answer to this question is going to be what we're going to go to next, and it's something called a Z-score. okay, or a z-score depending on where you are. Okay, so everybody, now we're going to talk about z-scores or z-scores here. Now, in the previous question, it's not possible to determine how many people got honors because we can't tell how far below the mean 80% actually is. Okay, so what a z-score is it's a form of ranking. Okay, and that really is. Okay, it is a ranking. So a z-score is a value for a particular piece of data. So we assign each data piece in the population a z-score. Okay, and it describes how far in terms of standard deviations that value is away from the mean. Now, just to kind of maybe before we get into this and start to use it, just to give you an idea of what we're trying to talk about here. Okay, let's say that you had a normal distribution, and this was the times for a marathon run. Okay, a marathon run. So we've got all the times here for a whole bunch of people run a marathon. We've got their times here, and now it's normally distributed. So watch this. Here's person A. Here's person B. Okay? Now, in your head, I want you to think about this. Who did better in the marathon? Was it person A or person B? Okay, think about it for a second. Most of the time, people are going to tell me, and I've done this in class, and I know this happens a lot. Most of the time, people go to B. Well, B clearly did better than A. And the question I ask is, well, why? Why do you think that? And a lot of times, it's one of two answers. Either because B is further along, or people say because it's closer to the middle. But that doesn't make any sense, okay? Because if you're running a marathon, you want to have a small time. Okay, you want to be further away. They do not give the award for winning a marathon to the person who came in the middle. Okay, they don't wait for the first, second, third, blah, blah, blah. Okay, there it is. There's the 100th guy, and we give him the medal here. It's the person who's further off, away from the mean in this direction right here, okay? We want someone with a time that's quite a ways to the left of the mean. Now, this can work in a different way as well. Maybe where the score, a high score, is important here. If this was in terms of, let's say, throwing javelins, okay, and along the x-axis was the distance, well then clearly B did better than A because he got a further distance, but still not really good because he didn't even throw up to the average distance yet. So there's this idea of ranking that's important here. Now, I want to give you another scenario here before we get into the z-score that might help clarify what we're doing here. Okay, let me just throw this out here. Let's say that you've got two different classes here, and you've got two students, Al and Bob. Oh, you can't hardly see that when it's blue on blue. Sorry, didn't think about that. Let me quickly grab another marker here, and we'll do that again. So we've got Al and Bob. Now, let's say Al and Bob both write their stats exam. Al, on his exam, gets a mark of 75%, and Bob gets a mark of 80%. Now, at first you might say, well, immediately, well, looks like, well, Bob did better. Okay, sure, Bob did better. Now, what if I told you, though, that the class average, okay, for both of these guys here, what if the class average here was 65%? And what if the class average here was 75%? Now I hope you kind of see where I'm going with this. Well, okay, hold on a second. In Al's group, he's a fair bit further away from the average than Bob is. Oh, okay, well now it's starting to look like, well, you know what? I know that his mark is lower than Bob's mark, but in the context of the class, he's actually done better than Bob did. But actually, this is still not enough information here. What we need is the standard deviation. Okay, with the standard deviation, let's say, for example, now that the standard deviation here is 5%, but the standard deviation here is, let's say, 2%. So this is now what I'm telling you. Okay, so here's the class that Al's in. Here's the mean at 65%. One standard deviation over is 70, two standard deviations over is 75%. Here is where Al is. Al is two standard deviations above the mean. Bob, on the other hand, the class mean here is 75. One up here is 77. Another one up here is 79. Bob is just a little bit more than 2 standard deviations above the mean. Now, we were talking before about how these cuts, this using of the standard deviation, cuts the normal distribution up into these nice predictable percentages. If that's true, the values down here really don't make much difference. What matters here is the number of standard deviations you are either above or below the mean. If the percentage here is the same as the percentage here, and the percentage here is the same as the percentage here, then Bob did better than a larger percentage of the class. So what we really need to know is how many standard deviations away from the mean are you? That is how we can compare to people. It is not enough to know what their marks are. It's not even enough to know what the average of the class is that they're in. You need to know that standard deviation. And that's what this Z-score formula does. The Z-score takes your data value, or the data value of a specific object, subtracts the mean from it, and then divides that difference by the standard deviation to try to get a sense of a bit of a ranking there. How do these objects compare to each other? So a positive Z-score indicates that value is above the mean. A negative Z-score would mean that you're below the mean. If, and we'll say here, if your Z-score is equal to 0, that means the data value is the mean. Okay, it's right on top of the mean. Okay, so anyway, let's take a quick look at an example here and see if we can make this make even more sense. Okay, so let's go back to the creative writing assignment. Okay, so here's our distribution. There's our mean, and if we go up and down by the standard deviations, you see those numbers there, the marks on the assignment. So we're going to ask, what is the Z-score for a mark of 76? Okay, so our Z-score here is if somebody got 76, then we subtract the mean from that and divide by 6. Okay, so that's going to be 6 divided by 6, or 1. Okay, so the Z-score for a mark of 76 is positive 1. Now that means to me that you are, okay, that mark is 1 standard deviation above the mean. Okay, now in a little bit here, in another lesson, I'm going to show you where you can grab the actual probabilities for that, so that we can actually figure out what is the probability that you are right there. Okay, and then you can use that to compare that to other data values here. But for right now, just get a sense here that this is 1 standard deviation above the mean. The Z-score, what is the Z-score for a mark of 58? Okay, so there's Z-score here. We're going to take that value here, 58 minus 70 over 6. Okay, well that's going to be, what is that, negative 12 over 6. So the Z-score here is going to be negative 2. This means that that mark is 2 standard deviations below the mean. Okay, so that gives me a good sense of where that value is located here. Down here, and this is that 80% that we were asked about just a little bit ago here. What's the Z-score for 80? Well, 80 minus 70 over 6. Well, that's going to be 10 over 6. Well, to the nearest hundredth, so this is going to be approximately 1.67. Okay, so this score is 1.67 standard deviations. Now it's positive, so that means above the mean. Okay, and that gives us a pretty good sense of where that is located, how that would be ranked amongst the other marks. Okay, now just to finish this off, and I know this has been a little bit more of a longer lesson here, but the idea is important, and where it leads to after this is going to be quite interesting. So in heights, the heights in centimeters of 5 starting members for the Grizzlies basketball team are 168, 184, 192, 195, and 213 centimeters. If the mean height is 190 and the standard deviation is 15, what's the Z-score to the nearest hundredth for the tallest player? Okay, well the Z-score is going to be that height, so 213, minus the average, 190, all over 15 centimeters. And when we do that, we're going to get a positive 1.53. Okay, now notice that there's no units here. Okay, and the reason there's no units here is because this is going to be centimeters minus centimeters divided by centimeters, and so those units cancel. So this is a dimensionless unit here. It's just a ranking. But this gives me an idea here that the tallest player is a little bit more than 1.5 standard deviations above the mean, and in a little bit that's going to mean something a lot more important. Okay, here's a really interesting question, and one that we're going to kind of come back to in a couple minutes here. The average mark on a science exam was 62. Okay, so the mean was 62 with a standard deviation of 11. So that gives you a sense of the spread of the data, how well the group did on that exam. If the marks were normally distributed and a student's Z-score was 1.53, then what was the student's actual mark? Okay, so remember your Z-score is the actual data value minus the mean over the standard deviation. In this case, it's the X that I don't know. Okay, so that's what I'm looking for. So first of all, to get the X, I would multiply both sides by the standard deviation. So that's going to get me the Z-score multiplied by the standard deviation will equal X minus the mean. And then to get X by itself, I'm going to add the mean to both sides. So this would be the Z-score multiplied by the standard deviation plus the mean is equal to X. Now, I can do that. That's going to be 1.53, the Z-score, multiplied by the standard deviation plus the mean of 62. And when you do that, I get 78.8% to the nearest tenth. And that's how I can retrieve the actual mark from that information, that statistical information. Okay, for this problem, a similar sort of problem, the one that we just did, just looking for a different value here. It says the weights of a large shipment of watermelons are normally distributed with a mean of 2.8 kilograms. The weight of a particular watermelon, so that's going to be an X value there, is going to be 2.25 kilograms. Now notice it's below the mean. So without even going any further, I suspect that its Z-score would be negative. And this is 1.01 standard deviations. Okay, so as soon as I give you that, I am giving you the Z-score. So it's going to be 1.01, and it does in fact say below the mean. So I know that that means it's going to be negative. We want to figure out what the standard deviation is. Okay, well our formula for that is Z is equal to X minus the mean over the standard deviation. So if I wanted to figure out what the standard deviation was, the first thing I would do would be to multiply everything by the standard deviation to get rid of that fraction. And then I would divide everything by Z-score. So the standard deviation will equal X minus the mean over the Z-score. So my standard deviation will be 2.25 minus 2.8 divided by negative 1.01. And it turns out to the nearest, what is that, tenth, that is going to be about a half a kilogram. I probably should put the units there. There we go, a half kilogram. Okay. Here's the question that I was referring to just a couple minutes ago, where I said that the marks up here, the question with the marks, we're going to kind of come back to that. I want to show you this here. You've maybe heard of grading on a curve. Never quite known what that was. This is what we mean by grading on a curve. So the marks on an ethics exam at a university were found to have a mean. Okay, so here we go. The mean is 47%, so not quite passing, with a standard deviation of 12%. The professor felt that the exam was too difficult and decided to adjust the original marks by raising the mean. Okay, so we're going to come up with our new mean. So this is, let's maybe put 1 here, we'll put 2 here. Our new mean is going to be 60%, and reducing the standard deviation to 10%. Okay, now, so the professor is going to kind of impose this on the set of data that he's collected. But what stays the same are the Z-scores. The Z-scores remain unchanged. Basically, your position in the group doesn't change. Your mark will change. Everybody's mark will change. The average will change. The standard deviation will change. The shape of the distribution changes a little bit in terms of how tight it is to the mean, but your position doesn't change. So what's your new mark going to be? Well, what we got to do to start off with is we got to figure out what our Z-score is originally here. Okay, so the original mark here was 35%. What we don't know is that final mark here. So the first thing we need here is the z-score, and I'm not going to even put z1 on there. And the reason I'm not going to do that is because that's never going to change. It's always going to be the same z-score. So we're going to take 35, and we're going to subtract 47, and divide that by 12. Okay, so 35 minus 47, just doing this on my calculator here, divided by 12. Okay, I probably should have looked at that a little bit more closely and realized what was going on here. So the z-score here is just -1. Okay, now that z-score is going to stay the same. So let's just take a look at what's going to happen here. So the z-score stays the same, but now what's going to happen here is we're going to look at these new values here. And we had done this before, okay, just previously. I want to figure out what the new mark is. So what I'm going to do is multiply up by the standard deviation. So it's going to be the z-score multiplied by the standard deviation. And now I'm going to add the mean over. So z-score multiplied by the standard deviation. I'm going to add the new mean to it, and that's going to get me that new mark here. So it's going to be -1 multiplied by the new standard deviation is 10%, and the new mean is 60%. So what did this student get here? Well, -1 times 10 is -10 plus 60. That's 50%. So this student goes from getting a 35% on that exam to a 50% on the exam because of this idea of grading on the curve and the fact that their position in the group doesn't change. I hope that makes sense. I hope you're starting to get a bit more of an appreciation of these tools that we're introducing.